Hi, welcome to this lesson on calculus, applications of the first derivative. Let's have a look at question 4. Again, we're given f prime of x, so we're given the derivative of a function f, and that derivative is equal to x squared minus 8x plus 15. Again, we want to classify any stationary points and intervals where the function f is increasing or decreasing. Okay, so the original function we're given f prime of x, that's the derivative, is x squared minus 8x plus 15. So for stationary points, we simply set the first derivative equals to 0. Okay, so this implies x squared minus 8x plus 15 equals 0. And I can most likely factorize this. So I think of factors of 15, that gives me a difference of 8. Well, 5 and 3, that would probably work. So let's try 5 and 3. Then we have x and x. Okay. But now to get a positive 15, we either need two plus signs or two minus signs. But because we want negative 8x, I would say two minus signs. Okay, so therefore I get x equals 5 or x equals 3. So again, we don't know the original function f, but we do know at what point on the x-axis will they have stationary points. And again, if we try to think about it logically, if this is a second-degree polynomial and we've already got the derivative of it, going backwards, this is most likely a third-degree polynomial, which is a cubic graph. Alright, so now let's look at the intervals of increasing. So again, that is when f prime x is greater than 0. So that implies that x squared minus 8x plus 15 is greater than 0. But this is a polynomial inequality now. So we need to get 0 on one side, which we do. Then fully factorize the left-hand side, which we've done here. And therefore list our critical values, which are our stationary points, x equals 3 or x equals 5. So on our number line, so here's 3 here and here's 5 here, we put open dots because we're not including them by the inequality. And again, I just take values in between each region and test. So if I take 6 minus 5 is 1, 6 minus 3 is 3, so it's going to be a positive number when multiplied. If I take a number in between 3 and 5, like 4, well, 4 minus 5 is negative 1, 4 minus 3 is positive 1, so it's going to be negative when multiplied out. And then if I take a number like 0, for example, it's going to be negative 5 times negative 3 is positive 15. So a positive region. Okay, but it's increasing on positives, so therefore the interval for increasing is x is an element from negative infinity up to 3, then takes a break, then joins up again, union, at 5 to infinity. Awesome. And then for the intervals of decreasing, right, we can see it immediately from the given number line from increasing. It's at the negative region. So that's x is an element between 3 and 5. Okay. So if again, we wanted a rough idea of what this would look like, So here's our xy plane. So at x equals 3 and x equals 5, on these lines here, those are going to be stationary points. So in terms of a cubic, it's most likely going to be turning points. And we know that from negative infinity to positive 3, the graph is increasing. So negative infinity all the way up to positive 3, the graph increases, reaches a maximum turning point, or a locally maximum turning point, I should rather say, and then decreases in the interval 3 to 5. So it comes down. It probably hits a turning point maybe here or even further down. We don't know exactly, right? So we're just drawing a rough idea of what it could look like. So it could go up to there, potentially, and then turn and then increase again on 5 to infinity. So again, these are just interpretations or a rough sketch of what the potential graph f could look like. But again, we see the shape of a cubic coming out. All right, and that kind of makes sense because the first derivative was a quadratic, a degree lower than a cubic. Awesome. That's how we would do this one. I'll see you in the next one.